Now I wish that pacemakers were infallible, and once implanted they never went wrong. Unfortunately, this is not the case. In this chapter, you will learn how to recognise the most common problems that occur and how they can be resolved. In many cases, a tweak to the programming is sufficient. Why is this so important? Well, I've known unnecessary surgeries to resolve problems that actually could have been solved with a small programming change. This chapter will ensure that you do not fall into the same trap. Failure to capture is when the output pulse from the pacemaker fails to make the target chamber depolarize. Let's have a look at this on an ECG. Here we can clearly see that the output pulse, which is represented by this pacing spike, has triggered a ventricular depolarization, and that is what we would usually expect to see. However, if we look at a few heartbeats along the ECG, we can see that this output pulse has failed to trigger a ventricular depolarization. When some of the output pulses are successful, but some aren't successful, this is intermittent. You can also have permanent or absolute or chronic failure to capture. And on the ECG example below, we can see that actually all of these output pulses that are represented by these pacing spikes fail to trigger a ventricular depolarization. And here I've just marked on for clarity all those events where the pacemaker has failed to capture. So, what is happening? Well, the pacemaker is delivering an output pulse, but it is failing to have an effect. This is usually a very bad sign, and I'd like to explain why. When we program an output pulse, we find the threshold of the tissue, and we make sure the output pulse is twice as large as the minimum amount of energy required to trigger a depolarization. So on here, I've made these numbers up. They're hypothetical values for the minimum amount of energy required to trigger a depolarization in the atria over time. And we can see actually that in the real world, the threshold does fluctuate. It's 0.7 volts at 0.4 milliseconds here. Then it might go up to 1 volt at 0.4 milliseconds, down again to 0.75 volts at 0.4 milliseconds, and even as high as 1.25 volts at 0.4 milliseconds. These slight fluctuations in the tissue's threshold is a very natural occurrence. The output pulse is always large enough to trigger the depolarization. Pacemakers are also cleverer than this. Although you may have set the output pulse to 2 volts at 0.4 milliseconds, the pacemaker has a safety mechanism to deal with the occurrence of a suddenly large threshold. So here we have some made up figures again, and all of a sudden the atrial tissue, for whatever reason, requires an output pulse of 6 volts at 0.4 milliseconds to capture the tissue. Again here, it requires 5.5 volts at 0.4 milliseconds and 6.5 volts at 0.4 milliseconds. Now these are hypothetical numbers, but if the threshold did suddenly increase, the pacemaker is smart enough to adapt. And what pacemakers usually do is just ramp up their output pulse to the max. In most pacemakers, this will be around 8 volts at 1 millisecond. And you can see that the pacemaker has recognized the problem, adapted, and we're still managing to cause the atrial tissue to depolarize. And in actual fact, the pacemaker is still performing. Now, this will be picked up at their next follow-up or in pacemaker clinic, and we can do something about it. The important fact is that this person will still have a healthy heart rate. So, if you are seeing loss of capture, which can be seen on this ECG here, you can be quite confident that something catastrophic has happened to the lead. And that is because the chances are the pacemaker has increased the output pulse to 8 volts at 1 millisecond, yet this is still insufficient, which could suggest we have an infinite pacing threshold. No matter how much voltage we are delivering, it is not going to make the tissue depolarize. So let's have a look at a few of these bigger problems which will lead to your failure to capture. We have lead displacement, a lead insulation break, or a lead fracture. Let's break these down. A lead displacement is where the lead has come away from where it is meant to be. These most commonly occur within 4 to 6 weeks of pacemaker implant. In this instance, we can see the right ventricular lead has pulled away from the myocardium and is now sat in the middle of the ventricle. Because of this, the output pulse is never being delivered to the tissue that is meant to. And this is quite a common reason for an increase in pacing threshold. Having said this, you can quite often still capture the tissue, but with much higher output values. Failure to capture could also indicate an insulation problem. Now, our pacemaker leads are insulated, which means that the electricity does not escape before it has reached the electrode. This is where we want the electrical impulse to leave the pacing lead, travel through the heart tissue, and then back to the other electrode, in this case the pacemaker. Now the problem is that electricity is inherently lazy and will take any shortcut provided to it. If we have an insulation break, the electrical signal sees an opportunity to take a shortcut. It will leave the circuit at the point of the insulation break and travel back to the other electrode. Again, when this occurs, the pulse output never arrives at the correct tissue, and so in this instance we would probably get failure to capture. The third lead catastrophe that can happen is a lead fracture. Now, in a lead fracture, the wire that runs down the lead has broken, and now there is a break in the electrical circuit. Now, remember, at this point it isn't possible for the electrical current to leave the lead because here is still insulated. So actually, the electrical current is just met by a dead end. Again, the pulse output never arrives at the correct tissue. So, your takeaway message? If you are seeing failure to capture, then it suggests a serious problem that may require the lead to be replaced or repositioned.